All right, y'all, welcome back. We're going to continue our introduction into linear regression. And so where we left off was just, the previous video we talked about, okay, how do we build this linear model, right? Pretty much how do we draw this line that best fits the scatter plot pattern that we see. And so we left off here where I'm just saying, well, we picked this line such that these errors between our line and observations are minimal. And the ones that we see given in StatCrunch and the ones that we'll calculate in the next slide, those are all guaranteed to give us the best y-intercept and slope estimates such that we minimize these errors. Okay, so in the previous video, we used this line to find the predicted height of daughter given the value of mother. So we were using it for prediction, and we're just saying, look, the big difference between algebra and stats is that this line is within context. So every numeric quantity that makes up this line here has significance to the study, right? Where y is the predicted height of daughter, it's really an average. X is the height of mother, and what we're going to do now is kind of explain what A and B mean within the context of the study. Okay, but before we do that, I just want to get into, we've just been relying on StatCrunch to give us the estimates for y-intercept and slope, and without really knowing too much how it's doing. But commonly we see these formulas here. If you want to find for the regression line y is equal to a plus bx, it's saying, well, given your data, the estimate for the slope is going to be your correlation coefficient times the quotient of the standard deviation of the outcome variable over the standard deviation of the explanatory variable. Okay, and for the y-intercept, it says, well, if you want to find the y-intercept, that you're going to find the average of the outcome variable values, and you're going to subtract the product of whatever we got for the slope and the average of the explanatory variables. Okay, so last time in class we said, well, in calculating correlation, it doesn't matter if you get the order of x and y mixed up, meaning we confuse what's explanatory variable, what's the response. Okay, but when we get into the regression line, it matters big time. Okay, so just to indicate, this y is for the response or the outcome variable, and this x is for the explanatory, the predictor variable. Okay, we don't want to mix those up. If we were to confuse these, we get some different answers here. Okay, but y is a response or outcome variable in the study, and x is a treatment, explanatory, or predictor variable. Okay, so s sub y is the standard deviation of the observations for y. S sub x is the standard deviation observations for x. Y bar is the mean of observations for y, and x bar is the mean of observations for x. And in StatCrunch, x stands for independent and y stands for dependent, right? Now obviously from this equation line, we see where that comes from, right? Right, y, the value of y depends on the value of x, right? This predicted height of mother depends on the predicted height of daughter depends on the given height of the mom. Okay, so let's continue here. Okay, let's put these to use. Okay, so if I had to use these equations, would they add up to what we saw previously that StatCrunch had just given us? Right, so in here you see I just did summary statistics, and I did it for mother and daughter heights. And so remember n here, that means these are the sample size, so it means that there's 1,375 mothers in the study, and of course there were 1,375 daughters in the study, right? And the mean height for the mothers was 62.45 inches, and the mean height of the daughters was 63.75 inches, right? And the standard deviation for mothers was 0.235 inches, and the standard deviation for the daughter's height was 2.6 inches. Okay, so remember the standard deviation, it means, well, if we were the typical or the expected distance between any height of mother and the mean should be about 2.3 inches, right? And same for the mother here. Okay, so it's kind of like the distance of observations we should see from the mean. Okay, and that's kind of obvious from our data here. Okay, and if we calculate the correlation between mother and daughter, we get roughly 0.49. So we've seen 0.49 before. We calculated that in the previous video. Okay, but all I'm going to do is, this is my R, right? This is my R. This value here is, since this is mother is my explanatory variable, this is my X bar, and this is my S sub X. And since daughter's height is a response or outcome variable, this is my Y bar and my S sub Y, standard deviation of Y. Okay, so it's very important we label those right away. That way, if we need to use these formulas, we know how to plug in correctly. Okay, so here's my correlation, standard deviation of daughter's height over standard deviation of mother's height. And that's what we get here. We get 0.54, which is what we saw in the previous slides. And if I were to calculate the y-intercept portion of it, well, this is the average height of daughter minus the product of whatever we got for the slope and the average height of mother. Okay, so what we get here is this quantity here, 29.92. So this is the exact same results. Of course, we rounded off some decimals here, but these are the exact same results that StatCrunch was calculating for us. Okay, so in this study here, right away I'm labeling. I'm saying, okay, what is Y and what is X? Okay, so obviously X is the mother's height and Y is the daughter's height. So I label them appropriately. Okay, so it really matters how we label these, because if we were to flip these, example for here, if we were to mix them up here, we get a completely different answer here. Okay, all right. So once again, if we were just to go back, if we have our regression line here, right? So remember, this is all within context, right? Every number we present is within context, right? So we need to be able to explain what the number means. Okay, so here we're saying predicted height of daughter. Oh, I guess we're doing it again. Predicted height of daughter. Okay, predicted height of daughter is equal to 29.92 inches plus 0.5 plus the product of 0.54 and the height of mom. Okay, or mother. Okay, so right here I'm just saying, well, this is how I calculated these, but what do these mean, right? What do these mean? Okay, so let's go in and find out what these mean. Okay, so in general, right, so we're just saying, how do we interpret the y-intercept and the slope of the regression line? Okay, remember all these numbers in context, right? So in general, A is the typical outcome for variable y, right, or the average outcome for variable y, given the value for the variable x is equal to 0, right? So that's just definition of a y-intercept, right? When x is equal to 0, we have A. Okay, we're just saying A is the typical outcome for the variable y, or the average, right? And for the slope, we're saying, well, because remember it's rise over run, right? So this B, quantity B, I could just write it as B over 1. And so what we say is, for every 1 unit increase in x, the typical outcome for variable y will change by the amount B. Okay, so let's interpret this within the context of the study here. Okay, so if we were to do that, pretty much what we get is, well, this, for the y-intercept, we get 29.2 inches. So what this is saying is, well, 29.2 inches is the typical or average height of daughter, given the mother's height is 0 inches. And you may say, huh? And what happens is that it doesn't make sense for this particular study, because we don't have any data that's close to x is equal to 0. So this is kind of called extrapolation, which we'll mention towards the end of this video, and we give it a because it doesn't really have any meaning for our context here. It doesn't make any sense because what's the chances of having a mother whose height is 0 inches? Okay, doesn't make any sense at all. Okay, so, but that's how we interpret it in this case. In other studies, it would make more sense if we had data that was near 0 inches or whatever x is near 0, but in this case it doesn't. Okay, now for the slope we can always use. Okay, and so what we're saying here, because we say for 1 unit increase, remember everything's in inches here. Right, we need to keep track of the unit of measurement here. So it says for every 1 inch increase in mother's height, okay, the typical height of daughter will increase by 0.54 inches. Okay, so what that's saying is that it's our rise over run. So remember the explanatory variable, which is on the x-axis, that's our run. So we're just moving over 1 in the x direction, right? So this is 1 inch increase in mother's height. Okay, so that's our run. So now we want to know, well, how much does the rise change? Well, that's what this value is here. Okay, so pretty much we're just putting b over 1. Okay, 0.54 over 1. Okay, so therefore, the y, the rise, which in this case is whatever we're trying to predict, which is daughter's height, okay, it will increase. And the reason it's increased because this is a positive number. If it were the minus sign out here, we say decrease. Okay, but there's a positive association going on here, so it'll increase by 0.54 inches. Okay, so it's kind of, we're getting more and more precise about the association between the two variables. At first we looked at the scatter plot and we said, okay, we see a positive linear association. Okay, great. Next we came up with the correlation coefficient and we said, oh, well, the strength of linear association is roughly 0.49. Okay, so this 0.49 indicates a moderately strong positive linear association, right? Then we took it a step further with the linear model. And what we said there with the linear model, we said, hey, well, you know what? For every 1 inch increase in mother's height, the typical or the average height of daughter will increase by 0.54 inches. So you see, we kept becoming more and more precise. First, just by analyzing the scatter plot, then by looking at the correlation coefficient, and now we have the slope. Okay, but it's very important that we can interpret all of these numbers within the context of the study. Okay. All right. So, anyways, this is just the StatCrunch output that we got from last time. And here it's just, dependent. Remember, that's the outcome or response variable. That's daughter, so that's correct. And the independent variable, that's x, the explanatory variable, it's at mother, that's correct. So we got to make sure those are lined up. We got to make sure that these are lined up where they need to be to make sure that we know StatCrunch is giving us the output that we want, right? And see, even they try to write it within the context. They're saying daughter is equal to 29.92 plus 0.54 times the product of mother. So see, they're even trying to write their model within context. Of course, we did a better job in our slides, but you see what they're doing here. And then sample size, there's a 1,375 observations or pairs, mother-daughter teams. And then the correlation coefficient was equal to 0.49, and we saw that before. Okay, this R square we'll get into a little bit later. Okay, but we'll see that there. And of course, these here we won't focus on too much. Pretty much we're looking for like this stuff, p-value, like less than something. But don't worry about that right now. Okay, don't worry about that right now. But these are just kind of validating. What these things are do is they're validating our model. Okay, because really we are estimating this quantity and this quantity here. We don't really know what they are. So we want to test to see whether our model is any good. Right, so that's what these are doing here, but don't worry about those too much. Okay. So really quick, one thing that we should be careful for is for slopes near or equal to 0. Okay, so if the slope were 0, then all we would get is a constant function. Okay, if the slope were 0, we would just get, you know, y is equal to the y-intercept, and that would just be the average of y. Okay, but we need to be careful. Okay, for linear trends, a slope of 0 means there is no association between x and y. Okay, so let's go back and look at the scatter plot we looked at last time, which was not age, not weight and running speed, but age and running speed, where there was clearly really no pattern there, right? We really didn't see any kind of linear association there. Okay, so some warning signs here is if we were to look at the scatter plot with the fitted regression line, right? If you look at this regression line, it's almost completely horizontal. Okay, meaning that the slope is very close to 0. Okay, so what that means is, you know, if we're doing, you know, our interpretation here, right, there's not that much of a change, right? This 0.06, that's kind of saying for every increase in year, for every 1 year increase, right, the running speed, right, will decrease by 0.06 miles per hour, and that's a very, very small change in comparison. And you see this estimate for the slope here. Okay, the slope of this red line here is negative. There's a minus sign here, but it's negative 0.06. Okay, so it's very close to 0. Okay, and so pretty much what we get is like a line that looks horizontal. So it's kind of telling you that given x, it doesn't really shed light on what the value of y could be, right? Given x, I get y's here. Given x is 20 years, I get y's here. Given x is 30 years, I get y's here. There's really no difference here, right? It doesn't, given age, it's not helping me to predict the running speed, right? And so our model, when that happens, right, our model will give us an estimate for the slope that's very close to 0. Okay, or maybe equal to 0. Right? So if we were to, because StatCrunch doesn't know any better, okay, it's just going to give you, right, these estimates here. Okay, but what we need to note is that since this b is close to 0, we will remain skeptical of our results. Okay, and maybe perhaps not use regression analysis for the study, since age does not help us predict a runner's top speed. Okay, runner's top speed. Okay, so we should be careful when we see things like this, right? And really we're estimating the y-intercept and the slope. We don't really know what they really are, but we're just making these estimates, and so these could be close enough to 0 such that, you know, we just don't trust this model. Okay, and we shouldn't given this line here, just given the visual here. Okay, and just go back a slide. You may have seen it here, right? Here, this is 0.54, right? I guess that's pretty close to 0. Okay, but these things here, they're doing tests. See, it says parameter estimates, analysis of variance. Don't worry about it too much, but I just want to point out that these here are indicating these p-values. We haven't heard of those yet, but they're indicating that our model is in fact good. So we would have to do this check in order to verify. Okay, but here I've checked it. I'm certain that that a linear regression is not needed here. Okay. All right. So as far as evaluating the linear model, so there's just some things that we need to, when we have our linear model, we just some mistakes we need to avoid and some things we need to check before we go further into our study. So the first thing we need to check is make sure that we're not using a linear regression model to model a nonlinear model. Okay, so we've seen associations in the scatter plots that were clearly nonlinear. Okay, so in the scatter plot we saw a clear association, a very strong association, but it was not linear. So we're just saying, hey, don't use correlation coefficient because it's not a good measurement for nonlinear associations. Okay, but you see, if say we went ahead and fit this line here, we try to force it here. Well, here, from here to here, we're pretty much overestimating, right? Because all the dots are below it. And then pretty much from x values from here to here, we're underestimating because all these dots are above it. And then from here to here, we're overestimating, right? Because all the dots are below it, right? So really these linear models are going to lead us to under and overestimate the typical values, right? And so we definitely do not want to use this simple linear model for these nonlinear models. Okay, but to model this type of association is no problem in practice. All we need to do is add an extra variable, but that's kind of beyond the scope of this class. But it's something that we can remedy really quickly using StatCrunch. The other big thing, right? So if you remember the syllabus in the back, there's a picture of some tombstones there, and some of the deadly sins you could commit in statistics. And here we've heard about this from chapter 1.4, but it says correlation is not causation. So a lot of times we can draw some very, very strong associations between two variables that may want one to think that there's a cause and effect association. But remember, an association between two variables is not sufficient evidence to conclude that a cause and effect relationship exists between the variables. No matter how strong the correlation or how well in the regression line, no matter how well the regression line fits the data. Okay, so because remember, this is an observational study. Whenever we talk about regression, it's an observational study. And with observational studies, we do not control who goes in treatment and control group. So therefore, we cannot establish cause and effect. All right, due to the fact that there could be lurking variables, unmeasured variables that are pushing this association. So I don't know if any of you heard of butter, okay, or margarine butter. It's a popular garnish that goes with toast and maybe tortillas too, if you like tortillas. All right. I recommend it with flour tortilla and scrambled eggs with chorizo. That's not a bad combination there. But anyways, these. So if we look at this plot here, what we did is within certain locations in Maine, what we recorded is for that location. We recorded the margarine consumption per capita in pounds, and we also, for that location, we also recorded the divorce rate in Maine per 1,000. And so what you see here is that as a margarine consumption per capita increases, the divorce rate in Maine increases, right? So there's a clear-cut association between the two, right? Meaning if I'm in a place where people are just chowing down on margarine, right? Maybe they just got into this fad of flour tortillas with margarine and scrambled eggs and chorizo. Everybody's eating it. But what I also know is that the divorce rate is going to be high. Okay, so there's a clear association, a clear pattern, and I can use this model. I just walk into somewhere, right? Find this margarine consumption per capita, and with that, I could give a prediction on the divorce rate in Maine. Okay, but there's obviously not a cause and effect association going on here. Okay, we cannot say that margarine butter is the cause for divorce. Okay, I don't even know how you pull that one off. Okay, but obviously there's plenty of lurking variables here that are pushing this association. But they give you something really silly here, really silly example, just to kind of state that this example versus any other one that you see in regression is going to give you the same results. Okay, it's like making the same comparison. Okay, this type of study here, it's observational. Okay, we cannot conclude a cause and effect. Okay. The other thing is beware of outliers. So outliers, right? We've seen outliers in histograms, right, or in dot plots, right? They're just points that are very far away from the others, right? So, and just remember that when we calculate the sample mean, we must outliers can have a big effect on the sample mean, and so we need to keep track of those, right? And remember that these lines here that we're drawing, these regression lines, are really just sample means, just spread all over the place, right? So outliers in linear regression are points that do not fit the trend or are far from the bulk of data. Okay, so kind of similar to what we're looking for in histograms. And so the thing is that these outliers, they could be influential, okay, if their absence from the data results in a change of conclusions. Okay, so what we do here is this red line. Okay, this red line is the regression line if all the data points are included. Okay, so what we do is we say, oh, you know what? There's an outlier here. Okay, is it influential though? Should I just ignore it? All right, or should I keep it there? So obviously this point is not consistent with all the other data. Okay, but is it influential? That's really what matters. Okay, it's definitely an outlier, but is it influential? Okay, because if it's influential, maybe I should remove it if it's just one point. All right. But so what we do is we remove it. We remove it, and then we just look at this data here, and then we fit the line. Right, and that's what this blue line is here. And so you can see why this point is influential, because the equation of the line without the point versus the equation of the line with the point, they give you two different lines, which are going to give us completely different conclusions here. Right? So at this point, we need to make a decision, right? I mean, is this point out here so inconsistent that we should just remove it? Right? Right? Because it's really altering the results here. Right? Should we just remove it? Is it a mistake? Let's see what we want to do here. Typically, we want to remove these, but we should just know whether they're there or not. Okay, so pretty much we have to fit the line twice. Okay. The other pitfall we want to avoid is extrapolation. Okay, so extrapolation is where I kind of tricked you earlier in the week on Tuesday, is where this regression line is really like a crystal ball, right? It's kind of like, given this regression line, we can predict, right? We can kind of see into the future and predict future outcomes. But unfortunately, we can only see within our data set. Okay, so here for these X values that range from here to here, right? So only from here to here am I good in predicting X values, right? I can only predict within here, right? And so because only from X values from here to say here, right? Because that's where it ends right here. Okay, I know that there's a linear trend. Okay, I observed that because I have the data that tells me so. Okay, but beyond this point, I don't have any data. Okay, so I do not know if this trend is going to continue to be linear or not. Okay, so that's what this line is telling us, is that really extrapolation means that we use the regression line to make predictions beyond the range of our data. And this is very, very dangerous. Okay, so the association could be non-linear for values, or maybe change the type of linear association beyond our range, right? So say if I wanted to predict a value that was out here, right? Obviously that's not in my range. My X value range ends here, and I want to predict for this X value. So if I do that, it means I'm assuming that the trend remains positive linear association, but I have no evidence whatsoever to back that up, right? As a matter of fact, it could be something like this, right? This could be really what's happening. Right, maybe this process that kind of plateaus off, right? Plateaus and it starts decreasing. We don't know that, right? But where I observed it, right, this little piece here, right, it appeared linear, right? But here, obviously, it's not, right? So we need to be careful not to do that, okay, to extrapolate, because we could make some serious mistakes here, okay? Especially if this was the truth, right? This would be the true expected value. Whereas if I'm extrapolating, I'm thinking of this, right? So there's a big discrepancy here. Okay, so we need to be careful not to do that. So that's just a kind of visual. Okay, so pretty much my data, my range of data here of X value, really we're talking about the X values here, the explanatory variables. Here they range from here all the way to here. Therefore, my crystal ball for looking into the future is just good for these values in here. Okay, these values in here. All right, so I'm doing that. That's called interpolation, right? Because that's the data that I have. I'm pulling off the data that I'm using, right? right? But if I'm going to use extrapolation, pretty much I'm assuming that this linear trend continues out here, and also here that a linear trend continues down here. Okay, maybe we could get away if we're very close, but if it's something very far away, we're taking a big gamble here by assuming that this linear trend continues, right? Because we have no data whatsoever to back that up, right? We don't know. It could curve out like this, or it could go, it could do something funny there. Okay, so be careful with extrapolation. Okay, just know that our regression line or our crystal ball, it's only good for predicting in the range of data that it was built from. Okay. Now the last topic that we'll talk about in chapter 4 very briefly is R squared, which is the coefficient of determination. Okay, the coefficient of determination. Okay, so the coefficient of determination is computed by squaring. Okay, by squaring the correlation coefficient R. Okay, and actually we can report it as a percentage. Okay, R squared, we could report it as a percentage. And what it does is it gives the amount of variation in the response variable Y that is explained by the regression model. Okay, so if we go back to the example of exploring daughter-mother heights, here we come back to this R squared. And pretty much if you do 0.49 and you square it, right, you will get this value here, roughly about 2.24. Right. And so what this means is that 24% of the variation of heights of daughters was explained by the heights of mothers, right? So kind of what it gives you, it kind of tells you, it's kind of like a goodness of fit measurement, and it's telling you how well your model explains the response or outcome variable, right? So this is saying that, hey, that this heights of mothers, right, it helped explain 24% of the heights of daughters. Now, is that, we're talking about a percentage here. Okay, so we're squaring R, so R is between -1 and 1. So obviously R squared is between 0 and 1, right? And what we're doing is we're converting it to percentage. So really this percent can range anywhere between 0 and 100%. And so 24% is obviously on the lower end, right? But like I said, in some contexts, 24%, it could be significant enough, right? It's a smaller number, but it's better than nothing, I guess. Right, and we could still use mother's height to predict daughter's height here. Okay. So what we talked about here in this section is we talked more about the linear model, and remember this linear equation. It's in context, so we need to be able to interpret it in context. And we also talked about just some common things we need to avoid in using these regression lines, right? Meaning, watch out for outliers, which could be influential. Correlation does not imply causation. Don't use linear on a nonlinear model, right? And of course, we just get into this very last thing, which is kind of a goodness of fit measure, which is the coefficient of determination. Okay, so the next example that I'll get into is in StatCrunch. We'll kind of go through a case study which involves heights once again. Okay, so I'll see you soon.